This is the notes on atomic structure. Here's a couple links that you might find helpful. I probably have them linked from my website as well. Alright, general information about the nucleus of the atom. Nucleus is the center of the atom, and it's incredibly dense. In fact, if it was the size of a grape, if you could blow it up to the size of the grape, it would basically balance out. If you put it on like a little balance here, it would balance out if you had 5 million cars on the other side of the balance. That's how dense the nucleus of an atom is. Alright, inside the nucleus we find two things. We find protons and neutrons. Protons are positive in charge, and neutrons have no charge. They're neutral. And what we find is that a proton has a mass of 1.7 times 10 to the negative 24 grams. And that's kind of an awkward number to use. So what we did is we said, let's let this many grams be equal to some new unit. And so we made up a unit called atomic mass units. So we said, let's let 1.7 times 10 to the negative 24 grams be equal to 1 atomic mass unit. And it's interesting that neutrons have actually the exact same mass. Neutrons have the exact same mass as a proton. Turns out to be really convenient for us because we can, again, use just one atomic mass unit. So if I have a proton and a neutron, I have a mass of 2. If I have 2 protons and 2 neutrons, I have a mass of 4. Interestingly enough, I mentioned this in class to my students that it ought to bother people when they see these nucleus of an atom with all these protons in it, because what they should be doing is flying apart. And it turns out that neutrons basically are the glue that holds these protons together, so they don't fly apart on us. Now, buzzing outside of the nucleus, I'll just draw a little quick picture here. So if I have the nucleus of an atom, buzzing somewhere around the outside of the nucleus of the atom, you would have an electron. Okay? Or if the atom is big, it might have more than one electron. And it basically doesn't have a mass. Well, technically it does, but the analogy might be something like this. If you're a semi-truck driver, and here's your semi-truck, and you have to go to the weigh station to find out if you're overweight on your semi-truck or not, and a speck of dust comes and falls on your truck, you're probably not going to pull over and dust off the speck of dust, because the speck of dust doesn't make that much difference in the overall mass of the truck. Well, that truck that we just drew is very similar to the protons and neutrons in the nucleus of an atom, and the speck of dust that we just drew, a black spot right here, is very similar to an electron. It just doesn't matter in terms of the overall mass of the atom. So basically, it doesn't have a mass, and charge is negative, and it moves at fast speeds around the nucleus. Okay, here I have a simple drawing of an atom, and I put in here 3 protons, 3 neutrons, 3 electrons. And so if we labeled those, it might look something like this. Let me zoom up on the nucleus. Let's let the red ones be the protons. So we'll let those be protons. And they have a positive charge. And they have a mass of 1 atomic mass unit. Let's let the blue ones be neutrons. And they basically don't have a charge, so I'll put a plus, minus, and just put a line through it. No charge. And they would have a mass of 1 atomic mass unit. Zoom back out here. The electrons right here on the outside, these are the electrons. They basically don't have a mass, but first let me write their charge. They have a negative charge, and they basically don't have a mass, 0 AMU. Okay. Now, if I asked you, what's the mass of this entire atom, which is sort of the question I had. Sorry, sort of the question I had right here. What's the mass of the overall atom? If I could put this atom on, again, a balance of some sort that read in atomic mass units, what would it read? Well, really all you have to do is look here. You know that each one of these has a mass of 1, right? So I have 3 protons, 3 neutrons, a mass of 1 each for a total mass of 6. Plus these don't have a mass to count, really. So 6 plus 0 plus 0 plus 0 means that this atom has a mass of 6 atomic mass units. So it has a mass of 6. Alright, well, protons, neutrons, and electrons make up all the atoms on the periodic table. So what makes them different? Well, if you looked at a periodic table, and I recommend that you either look at one online, or if you want, you could turn to the periodic table in our textbook, and you'll find that every element has a box. And if we try to figure out what's the difference between all of the elements, well, there's really one thing that makes them different, and it's the number of protons. And so if you look, 6 protons is always going to be carbon. 8 protons, always oxygen. 1 proton, always hydrogen. Okay? And so we find that number actually on the top number on the periodic chart at the top of every box. And so the top here always tells you how many protons an atom has, and that tells you the kind of atom that it is. So if you go back to the previous drawing that we did just a minute ago, you should now be able to identify this atom, because you're just going to look basically at the number of protons. None of this other stuff really matters. So we look at the number of protons here. I think we said red was going to be protons. So I have 3 protons. So if you go to a periodic table and you look at your periodic table, look at the boxes and find which one has 3 at the top of it. And you'll find that it is lithium. Lithium always has 3 protons, so this is lithium. Now it turns out that if I had an extra neutron in here, 3 protons and 4 neutrons, it's still lithium because it has 3 protons, and it's the protons that identify the element. In fact, the number of electrons doesn't even matter. If I had an extra electron here, just throw an electron here, actually the charge of the atom now would be -1 because I have 1 extra electron compared to the protons. But the atom itself would still be lithium. So it's always the protons that identifies the element. Alright, now if we look at the periodic table and you find W on there, you're going to find at the top of the W, you find a number. You're going to find that it's 74. Okay. 74, again, tells you the number of protons, and it does, in fact, identify the element. And we call this number the atomic number. Now, at the bottom of the periodic table, we find the mass of the atom. And the mass of the atom, if you go to the periodic table and look up W, you're going to find it says 183.8. I'm going to explain a little later why it's a decimal. For now, we're going to round to 184, and we're going to use that number. So that's the mass of the atom. And again, the mass is the total protons and the total neutrons. Well, we know the total number of protons is 74. But nowhere on the periodic table does it tell us how many neutrons. But using some simple math, we can actually figure that out. Let me zoom out just a little bit. Okay, put this over here. So let's take a look here. If we know the number of protons is equal to 74, and we don't know the neutrons because it doesn't really tell us on the box for W. By the way, W is tungsten. You might be asking yourself, why tungsten when the symbol is W? And that's because this is the Greek, I actually don't know what W technically stands for. This is the Greek or Latin root word symbol most likely. In America we use tungsten as the common name. This is pretty universal. The symbol is universal. We find it pretty much on every periodic table in most countries I know of, but the common name may be different. So that's why there's a difference here on some of the elements. All right, back to what we were talking about. We actually don't know the neutrons from that, but we do know something about the mass of this atom. the mass of the atom includes only two things. It doesn't even matter the electrons, because electrons don't have a mass. It includes both protons and neutrons. Right? And if we look at the number that we have here, we see that it's 184 for the mass. So I'm going to write 184 down here. Well, we know that the number of protons is 74. So 74 of my 184 must be because of protons. And the only other place we get mass from is from neutrons. So it's really, really simple to do. All you have to do is subtract the number of protons from the overall mass, and you'll know the number of neutrons. So I take 184 minus 74, and I end up with... sorry, I think we had a slight glitch there, so let me restate that. We know we have 184 protons plus neutrons. We have to subtract our 74 protons from that, and I'll end up with the number of neutrons. So we end up with 110 neutrons. So you just subtract the two numbers. You subtract the mass number from the atomic number. You end up, or the other way around. You subtract the atomic number from the mass number. You figure out the number of neutrons. So an isotope. Isotopes, basically, we're dealing with the same type of atom. In other words, we're dealing with two versions. I'll use carbon as an example. There are several versions of carbon atoms. So you might have carbon, for lack of a better word right now, carbon A and carbon B. Now, we don't really call them carbon A and carbon B, but if I had two types of carbon, we'd call those isotopes. And what makes an isotope is that if it's carbon, it always has the same number of protons, because carbon always has the same number of protons, has 6 protons. But the number of neutrons can vary or change. They basically still have all the normal characteristics of an atom. However, they're radioactive oftentimes, or some of them. Not all isotopes are radioactive, but some isotopes can be radioactive because they emit or throw back out particles from the nucleus. In other words, they throw out protons or neutrons back out, and that's radioactivity. All right, we're going to talk about isotopes, and before I talk about them in terms of the notes in your paper, I'm going to give an analogy I gave in class. What I have on the picture here is a pen, red pen here, 2 blue pens, red pen here, 2 blue pens swaddled in black cloth. And I said, hey, imagine you went to a new island and you discovered a new element on this new island or a new universe, and let the red equal the number of protons. Well, these both have 1 proton, so they are the same element because protons identify the element. So I have 1 proton here and 1 proton here. So these are both the element pandemonium. Pandemonium. Okay, so I have an atom of pandemonium and another atom of pandemonium. But notice this one has a blue pen next to it. That would be a neutron. And this one has 2 of them next to it. Those are 2 neutrons. So this one has a mass of 2, and this one has a mass of 3. They're both the same element, 1 proton each, pandemonium, but they have different numbers of neutrons. And that affects their mass. So this one has a mass of 3, this one has a mass of 2. These are what we would call isotopes. In other words, they're the same element. They're the same element because they both have 1 proton, but they have different masses, and they have different masses because they have varying numbers of neutrons. So, isotopes are elements of the atoms of the same element, pandemonium, but have different numbers of neutrons. They basically have the same properties. You wouldn't really be able to tell them apart from each other. Aside from the, well, if you looked at the outside, you couldn't really look inside. You could only look at the outside. You couldn't see this. That's the inside of the atom. All you can see is the outside, the black. Basically, they look the same, and they pretty much act the same. The only thing is that sometimes isotopes with more neutrons are radioactive. In other words, they can shoot out their extra neutron, and that is what radioactivity is. And this one right here could eventually become just like the one I drew over on the right. Okay. Now, the periodic table, let me erase some of that. If you looked at the periodic table, if you look at the bottom number of the periodic table, this number down here on the bottom for everything, you'll notice it's a decimal. And that's because what we do is we take all the atoms in the universe. Here we have 3 of these, a mass of 3 and a mass of 2, and we would average those. And you would get an average of 2.5 when you average those. That's the mass number they put on the periodic table. Okay. All right, now let's go to your notes. All right, oxygen has 2 main isotopes, and we're going to draw those. So you go to your periodic table, and let's put in the important information. So if you go to the periodic table for oxygen, you find that this is 8 up here. You have O here for oxygen, and this down here says 16.0. Okay, we're going to draw this. This is called oxygen-16. We name an isotope based on the mass of that isotope. So, and this happens to be the most common isotope. That's why this is so close to exactly 16. Right? So if we drew that, the way we draw an atom in here is you tell me how many protons it has. It has 8 protons. You tell me how many neutrons it has. Remember, you take 16 minus 8, and you end up with 8 neutrons. Okay, 8 protons and 8 neutrons. And then to draw the electrons, we need 8 electrons. So we're going to draw a dashed line around here. And you can technically draw it solid too. I like to draw it dashed. And I'm going to switch colors, and we're going to add electrons. And the way we add electrons is the first shell can actually only hold 2. So we draw 1 up here, we draw 1 down here. Now this atom has 8 electrons because it has 8 protons. The first shell can only hold 2. The way the electrons are arranged is in the first shell they can hold 2, in the second shell they can hold 8, the third shell they can hold 8, and the next shell they can actually hold 16. Okay. So in this class we really only need to worry about 2, 8, and 8. So the first shell is 2, next shell is 8. So I need some more electrons. So I'm going to draw another shell around here. Not very neat here. And add my other electrons. So I'm going to add 1 here and 1 here. So you go down, and then I usually go to the left and then the right. And once you have 4 in a shell, they start to pair up. So I need 2 more electrons. 1 here and 1 here. And then usually you write down how many electrons are in each shell. So you'd write 2e negative and then 6e negative. And notice that that totals 8. Okay, so 8 electrons. All right, so we just drew oxygen-16. Let's draw the next atom. All right, we're going to draw oxygen-17. All right, and so notice the mass went up. If I looked at the periodic table, again, this would say 8. And this would say 16.0. But some oxygen actually has a mass of 17 instead of actually 16. Okay, so to draw oxygen-17, it's going to look identical to your previous drawing. So we're going to draw the nucleus of the atom, and inside the nucleus of the atom you have 8 protons. But it doesn't have a mass of 16 this time, it has a mass of 17. So I actually need 1 additional neutron, so I need 9 neutrons. Now 9 plus 8 equals 17. This is oxygen-17. And then we need our electrons, so I'm going to draw my dashed line down here. Okay. And I can add 2 electrons to that shell. 1, 2, 2e negative. Draw another dashed line. And put our electrons on there. Okay, we need 6 more again. We want 8 electrons. 1, 2, 3, 4, 5, 6. So that was 6 more. 6e negative, and then I can just count here, and I see 6 plus 2 is equal to 8. Good to go. So those are isotopes: oxygen-16 and oxygen-17.